So in the last two lectures, we have discussed two important concepts. One, the concept of mechanical impedance. So let me just revise. What is mechanical impedance? It's basically the force at a point to the velocity measured at that point or some other point. So if the point is different, then we call it as cross impedance. Alright, and if it's at same point, then we call it as drive point impedance. That is, the force is applied at one point and the response is also measured at the same point. Of course, we would be using the subscript ij. So I stands for where we are applying the force and j where we are measuring the response in terms of the velocity. So now if we are plotting the impedance, so impedance is a complex number because always there will be a phase difference between the force and the velocity. So if we are plotting the magnitude with frequency, so we'll have a plot similar to FRF. So only difference will be that the peaks, they will not signify resonance. The resonance will be signified by the troughs. So these minima, the points of minima, they specify basically the resonance frequencies. Alright, so this is clear. So we have discussed further the concept of mechanical impedance, that with this notion we can find out the mechanical impedance of simple members like damper, spring and mass. So we have just used the first principles because in the case of a mass, force and acceleration, they are related by mass, and that principle we are using to find out the actual value of the mechanical impedance. Similarly for the damper and for the spring. And now in the conventional system where we are showing a single degree of freedom like this, in the case of the mechanical impedance concept, we'll show these three entities in parallel. Okay. And then we also utilize the phasor diagram to find out the resultant value. I hope this is all clear to everyone. So we also derived that in parallel the impedances are added, and in series they follow the other rule, that the inverse of the equivalent is equal to the sum of the inverses. Okay, that was the concept of mechanical impedance. So after this, let me share the other presentation on the Liang's model. Of course, both these lectures we had done in direct classroom form, the blackboard form, but here I have presentation also, so I'm just recapitulating using the presentations. Let me open the other one, just give me a couple of minutes. So is my slide visible?
Not yet, sir.
Not yet?
No, sir.
Now is it visible?
No, sir, it is not visible yet. Yes, sir, yes.
Now okay, visible now? Okay, there is a lag, small lag. So just bear with that. So we have completed in the previous lecture complete 1D formulations of the EMI technique, the relationship between the admittance, electrical impedance and the mechanical and other electrical parameters of the P-ZT patch. So when we say mechanical and other electrical parameters, we mean that we are taking into account the mechanical impedance of the whole structure also. And what were our assumptions? We are considering only 1D interaction we are assuming that the force transfer is happening at the ends only, but the true one is through the medium of the adhesive. So adhesive, the actual behavior is like this, that if we are using as a sensor and if you are applying stress on the structure, then this is how the deformation will happen. So the strain undergone by the structure will not reach exactly to the piezo patch. And similarly, if the piezo patch is acting as an actuator, that is, the piezo patch is exerting force, then the strain in the piezo patch will be different from that induced on the surface of the structure. So this phenomenon is called as the shear lag phenomenon. So our assumption is that this is how we are idealizing the system. Okay. Of course, we are also ignoring any kind of bending of the piezo patch. Then piezo patch is infinitesimally small as compared to the host structure. So the points 1 and 2 here, the points of attachment, they are almost at the same point because the structure is very large as compared to the piezo patch. So this is how we are doing the modeling. So we are taking advantage of symmetry, and we say that the nodal line, it passes through the midpoint of the piezo patch. Okay, so we then use this model to just derive our value of the electrical admittance across the piezo patch. We have defined the axis like this, and once we are obtaining the value, we are just multiplying by 2, factor of 2 comes. So in the original, if you see the original derivation of Liang, he has derived for only one half of the patch. So we have derived for the entire patch, that's why there is a factor of 2 here. Okay, so let me skip few slides and take you further. So the derivation was very simple. So we had derived from the basic governing equation, differential equation, we had derived from the equilibrium of the small infinitesimal element of the piezo patch. So from there we went on. We have included the mechanical damping in Young's modulus of elasticity. So it's included there itself. So when we solve this equation, we get a particular solution like this. So first of all, by taking advantage of the boundary condition, we are eliminating the constant B, and then our equation becomes simple. So because B is 0, then finally we are expressing strain in terms of the displacement and velocity also in terms of displacement, and time, of course, time is there in both these expressions. So we have the expression for the velocity and we have the expression for the strain. So we are using this to get the constant A by this boundary condition, that at the other end of the patch we are just enforcing our definition of mechanical impedance. So why there is minus sign? Minus sign simply signifies that if there is positive velocity, that will lead to compression. So we have derived this. So with these substitutions, we got an equation by making use of the piezoelectric converse effect. Sorry, this should be read as converse effect. Let me just correct this. D is still there. So So we make use of the piezoelectric converse effect, and we are substituting here the expression for strain, and with that in account we can derive the value of the constant A, and then we have used the definition of mechanical impedance of the piezo patch. So this is the mechanical impedance of the piezo patch, and once we substitute this we get the constant A. And then the last step is we have to make use of the direct effect equation. So we have to substitute the expression for the stress, and we get the charge in terms of our previously derived expressions. And if you integrate the charge over the entire area of the piezo patch, you will get current. So current, instantaneous current to instantaneous voltage, that is what? That is the mechanical, that is the electrical admittance. So this is the expression we had derived. Now we'll go a little bit further, some very simple points associated with that. So I hope each one of you can derive this equation. So this part, this is the capacitive part. See, this part, it does not play any role with structure. The structure part is the other one where Z is coming into picture, because this part that signifies the structural interaction. Okay, so this part, it does not change. If damage occurs on the structure, then this part will remain same. So it's the other part which takes into account into the phenomena of damage is identified only because of the change in the second part. So in fact we can separate this equation into real and imaginary parts. We'll see today how we can do it, and then if you are able to separate this into real and imaginary parts, we'll show you in detail how we can do it. Then you will be able to see that the magnitude of the capacitive part is very high, and the capacitive part, it dominates in the susceptance or the imaginary part. So susceptance or the imaginary part is dominated by the capacitive component, and the real part or the conductance, that is dominated by the structural part. So now we are showing something called as quasi-static sensor approximation. So this happens if we have very small frequencies say 1/5 of the resonance frequency, then this term 10 kL by kL, that will be equal to 1. Okay, by just the limits you can substitute this and we'll have a very simplified expression. So this is called as quasi-static sensor approximation. Okay, so this also has applications, and then we have the expression for the mechanical impedance of the piezo patch. So this we can use for obtaining the natural frequency of the piezo patch also, resonance frequencies. So what happens at the resonance frequency? So basically resonance frequency is that frequency at which this will be minimum. So this would be minimum. When it will be minimum? When 10 kL by kL, in fact you can multiply both the top and the bottom by L, so 10 kL by kL. So 10 kL is infinite. If 10 kL is infinite, that point your ZA will be almost 0. So which is that frequency? That frequency will be the frequency which is in multiples of pi by 2, or multiples of pi by 2, 90 degrees to 170 degrees and so on. So that's how we can obtain the resonance frequency of the piezo patch. All you have to do is now here substitute the expression for kappa, or we can use the symbol K also. Here I am using the symbol kappa, and that expression will have omega also, and you will be able to find out the resonance frequency of the piezo patch. So it's your homework. So if you have a piezo patch of grade 151 PI ceramic, the sizes are given for 5 mm and 10 mm, then you will be able to do this. At least homework 1 you can do, homework 2 is not necessary. So you can also plot, if you work out with MATLAB, you can even plot the complete mechanical impedance as function of frequency. So homework 2 is not necessary. Homework 1 you can do. You just substitute here n equal to 1, 2, 3, 4 and so on, and you will be able to obtain the resonance frequency. So if you by chance obtain plot will be something like this, that here we are showing the real part, imaginary part, and this is the absolute value. So now the absolute value is minimum at those frequencies. So those frequencies, they are the resonance frequencies, and correspondingly the frequencies where the value is maximum, they are the anti-resonance frequencies.
So thank you very much. I hope that your holidays are going well.
So if you have any doubt on what we have covered, please let me know. If you have any doubt on what we have covered in last 2 lectures, please let me know, then we go further.
Sir, I have one question.
Yes.
Sir, in last lecture, we derived D3 is equal to epsilon 3 into E3 naught into e to the power j omega t minus delta. Actually, I'm not understand this expression where it is going to use.
This expression we have derived, but you understand the derivation? How we have derived?
Delta is equal to dielectric loss factor, yes.
Yeah. So this part comes in the direct effect equation. Direct effect equation, if you see, what is the direct effect equation? It has 2 components. The first component is this, that because of the dielectric effect, there is accumulation of charges. So the first part is on account of this. Then it has a second part also.
Okay.
Right? Shall I share the screen and show you where this comes?
Yes, sir. Yes, sir. Yes, sir.
Yes, I'm just sharing the screen. Just hold on. Let me just share the screen.
Here we have also mentioned that dielectric loss factor is equivalent to electrical damping also.
Dielectric loss factor is like the electrical damping. Sorry, I have shared the wrong one. Let me unshare. I hope the screen is visible to you.
Yes, sir. Yes, sir.
So if the screen is visible, then this is here we use this equation in the equation for the dielectric for the direct effect.
Yes, yes.
So what is the origin of the first part? Origin of the first part is basically the action like parallel plate capacitors. In parallel plate capacitors, you apply electric field, you see the accumulation of charges. One port becomes plus, other becomes minus. And what is the origin of the second part? The origin of the second part is stress. You are applying stress, that also produces charges. So the two effects, they are basically additive in nature. We are superimposing the two.
Okay, sir.
We are waiting for.
Alright. So any other question if you have related to what we have covered? Because today we'll be covering something new. So today we'll be covering something new, and before that we want to discuss about the visit. So I'm giving the charge to Dr. Dhawan to discuss about tomorrow, and we finalize everything, the meeting point and everything.
See now, dear friends, you have to go tomorrow and assemble there at 10:30. Your
Major Anu know everything in detail. You have to follow his instructions. Meet there wherever you have been asked. Don't be late. And the project manager has already interested one gentleman. His name is already known to Colonel Anuj, Major Anuj. So first of all, I would suggest that you ask the person concerned. They should explain you there at the assembly point about the bridge itself. And then secondly, where have they put the sensors? Thirdly, where are they, how they are using those sensors? Which is the data they are collecting? Where are collecting those data? And then how they are using that data in the structural monitoring. These are the basic things you can make questions and ask him. And then see the overall bridge. It is just about half a kilometer distance, and both sides are approaches. The flyover will be there. The entire bridge of this 500 meters is resting only on one sport. And that the height of the pylon is about 1.5 times that of the Qutub Minar. The entire structure to stay, and then further the load will be going down to the pier, and through that the foundation. Try to understand the basic behavior of the structure also, and more important is how they are put the sensors, how they are going to use those sensors. That is the point of your knowing information about that. And then you can put the question that the bridge life would be, say, 100 years or 120 years. What is the mechanism of that? That they will be collecting data, using this and monitoring this. Is there any baseline signature? I mean, for the undamaged structure? Now the time is moving. The data is also being collected. It's a continuous process. Like your EMI technique, once you start, the data goes on. So then how they will be using that data in the working of the damage part of the structure. Whether they have put strain gauges, they have put temperature, so what type of sensors they have put, and where they have put, why they have put those locations. These are the basic things you should try to know. And then all of you have to write, submit a report independently, so that we know that you are really making use of this time and have some value addition during your course on structural monitoring. Any other thing that you want to ask, you are welcome.
Major Anuj, the meeting point is the site office, right? The location which you
yes,
sent.
good evening, sir.
Good evening. It's the exact location of the site office. It's not the bridge,
That's
right?
very right, sir.
You have confirmed
Yes,
from
Not
the person, right? So we
Yes,
are
sir,
first
I'm
assembling at the site office. So it's basically office. It's not the bridge, and they will show us maybe some PPT or something. So let me tell you frankly, in 2017-2018, their structural health monitoring system was not operational. So we had gone there, and with the hope that we'll see the structural health monitoring system. But then they were more interested us in showing the features of the bridge, the structural engineering features, but not the structural health monitoring system. So I will confirm. I try to call the concerned executive engineer. I think Major Anuj has given me the number. He has not picked the phone. So I would confirm that we are going there for our purpose, for the SHM system, and the person, he is competent in explaining the SHM system. So that's the point I would ask. So if Dr. Dhawan, if you can also call that person, the executive engineer.
Yes, Major, you give me the number of executive engineer. I will also talk to him separately.
So we are meeting at what time, Major Anuj, or time you have given?
10:30. 10:30 morning. Morning 10:30.
Okay, so everyone can hopefully reach there on. So actually in the previous years we were booking the bus from here, but given the situation, so we are asking everyone who are around, they can go there individually, and those who are not able to go individually, they can be online. So someone will be doing the online recording. So you have to make sure that it will not be desktop recording. So organizer has to press the auto record button also. Okay, so that also has to be done.
You just text me exchange number and name. I will also talk to him separately.
Right, sir. I already texted you. I will send it again, sir.
That